Welcome to this short video where we're explaining to you how we might produce certain um, text highlighting files. Let me explain to you what I mean by them. I am going to go into my main story folder output essentially. Let me show you some of the output over here.
In a lush forest beside a serene river, a group of animals often met for their daily gatherings. The forest was
Okay, so we want to produce vertical portrait and P4 files like this to embed in a storybook template in an HTML code. Of course, this is how we produce these books, and then we want to uh, we want to get these off as I put. Um, on the right hand side, we have the still images, which act as a visual aid. Now, this can be achieved manually. I'm just going to open up a slide presenter here, for example, Google Slides. And what you do is you take the text of your page and you just paste it onto separate slides. And on each of the slides, you highlight three words at a time in uh, yellow color. But this is, of course, a very, very slow method, very time consuming. And then you have a further difficulty because you also have to export these JPEG files and then align them with an
moral.
audio transcript. Uh, and this can be done in a video editing software or application like Clipchamp or Filmora. Of course, all of this is quite painstaking, and it's better to just automate this process. Let me just show you what I mean. For example, if you're manually doing this, you have to listen to the track.
Moral. Sharing brings happiness and strengthens bonds of love and friendship. Story. In a small town in India, lived a
So, so as you can see, what we just did right now was we mapped the ends of each of these slides to the relative endpoints of the words in the audio file. Of course, can be done. It's a manual procedure, but it's not feasible for large scale production. That is why it is much better to use Python scripting. Python has the ability to reduce JPEG portrait slides, which can then be embedded into PowerPoint. Python also has the ability to listen to audio transcripts and find the start and end times of words. And finally, most importantly, it has the ability to control transition on PowerPoint. So it is because of all these features of Python that it's better to just automate the system and start producing text highlighting files through code. I will show you how this is achieved actually in now the coming sections. Okay, so here in this part of the video, we're going to explain to you how the text matching algorithm works. We need to maintain this directory called the complete build directory here. It contains the seed of our script, which are the text files here. These text files contain the text that is to be presented on every single page inside separate directories for each story. Um, these text files then go on to produce the audio files here. As you can see, we have weighted files that are produced using Google Voice API. And then also we have, most importantly, we have these PPTX files without transition embedded into an output main directory for each story. What you have are these PPTX files that uh, um, depict three words at a time being highlighted on the page. Let me just show you what I'm talking about right here. As you can see over here, it produces files without transition, PPTX files. This is being shown in uh, Google Slides, and it highlights three words at a time, as you can see over here. Um, Now, the important work over here actually is all taking place in these transition Python scripts. This is where the bulk of the action happens. And these apply transitions to the PCX files in our output directory, and then they go and sit in our transition main folder. Okay. So over here, we've developed a couple of different files to do this, couple of different transition scripts to do this. But trial and error is one of the best one is of course transition query. Form simple. The algorithm starts by actually first listening to the audio transcript, which happens here in this transcribe audio function, and it will return the audio transcript of the wave file that is fed into it. It is going to find the start and end time for the different. It's going to find the start and end time for the different words. Okay, it applies it here in this function here or in this line of script. So it gives you start time and of course the end time. So our text matching algorithm here, which occurs in define apply slide transition, what it does is that it compares the audio transcript to the real true transcript as required from the text file. It matches every third word in the true transcript to the best possible match in the audio transcript. That is done using, of course, the phonetics match, the semantic similarity, and of course also our Levenshtein distance embedded into the approximate match function. Phonetics applies a 4-digit alphanumeric code to every single word based on its audio recognition, and we have also semantic similarity, which gives the score at 100% in terms of the match between two words. Finally, there's also for us the Levenshtein distance, which calculates the distance between two words in terms of the number of delete and insert new letter steps that have to be taken. So we have these top three cases, top three LF conditions that will match every third word in our true transcript with words or best possible matches in our audio transcript. The first case is, of course, if there's an exact match between the third word and a given word in the audio transcript. The second case is where there's a phonetics match and there's also a semantic match. And the third if condition or the third LF condition checks if there's a precise phonetics match and also a strong Levenshtein distance match of less than or equal to 1. The reason we use phonetics as a passing condition twice is because phonetics has been shown to give the best results as compared to semantic match and the Levenshtein distance. How do we make sure that a given word which duplicates in the true transcript does not match incorrectly to any given word in the audio transcript? That is through a simple marker called K0, which matches when there is a given match in these top three cases. And then we have our running counter, which is K, for the word in the transcript to be matched, and that one, or rather the true transcript to be matched, and that one is then compared with, it's checked to see that it's not too far away from K0, at least not more than 6 steps away from K0. We then also have to consider how to handle the fail cases, but that is done separately. Okay, so let me just quickly mention now how we update values every time we have a pass condition. So the three main pass conditions were when there's an exact match between every third word in the true transcript and the audio transcript, and the best possible match in the audio transcript, and then of course the other two were phonetics with semantic match and phonetics with the Levenshtein distance embedded into the approximate match function. So every time there is a match, we set the selection start time to be equal to just the value of the start at that running counter K1, which is nothing but K crushed by modulo L. And of course, we do it modulo L so that it doesn't run out of bounds of start one. Start one is nothing but the start times of our words in our audio transcript. Okay, and of course we update heuristic start times. Similarly, heuristic start times are only used as a filtration later on to filter out values that are too abnormal. Also, we have value which gets updated to the same as the selected start time. That's when there is a match. When there's not a match, then value gets updated differently. Of course, also what happens is that we update W by 1 and our running counter K by 1. A running counter K by 1. K starts at 0 and W starts at 1. Okay, now in the case where there's no match, what happens is we've already mentioned, we are going to mention right now, our value is updated by max cap, heuristic start time, and both selected start time get updated to the value of the start of k naught plus 3x, 3x being 3 times the number of consecutive errors. Crushed modulo L, k naught is a marker for matches according to our 3 match cases, exact and these 2 split cases of phonetics with semantic and phonetics with the Levenshtein distance. Okay, so let me just explain to you what we do with the cases where there are fails with our first 3 passing conditions. Let me remind you what they were. The one was the exact match. One was the match between phonetics and semantic match, and of course one was phonetics and Levenshtein distance. So there's this fourth case where none of these passes work. So in this case, what we do is we just we use certain important parameters to essentially heuristically calculate what the selected start time should be in that particular case. Of course, I'll remind you that whenever there's a pass, we set the selected start time to be equal to the start time of that particular k value, k1, which is nothing but k crushed by modulo L, but we ensure that it lies in this bound of between min cap and max cap from value. Value is of course the selected start time of the previous word that got matched, or the one that the previous word that was considered for a match. What happens here is that we have 3 important parameters. One is mat. Mat is set to be equal to true only when there's an exact match, but in all other cases it's set to be false. This mat then gets used to decide how our running counter of k on our true transcript is updated, and we also have that if match is true, then we just update k to be the previous exact match plus 1, and if it's false, then we update it to be at least greater than both 3w minus 4, the current word being considered, and x plus k naught minus 5. This ties into what the value of x is. X starts off as 1 and is set equal to 1 in all cases when there's a match, according to these 3 top conditions, the 3 LF conditions that we mentioned. But in the case of every time there's a fail, we increment x by 1. So x essentially counts the number of consecutive fails that we have, and that is used to update k in the case where there's a fail. So we ensure that x is at least 3w minus 4 and x plus k naught minus 5. So that we're not too far away from our previous position marker of a heuristic match of k naught from the first 3 top LF conditions. Also, finally, we have that reflected start time is calculated heuristically. Value, of course, any reminder here, value gets updated as value to the max cap. We don't try to calculate value heuristically, which is the previous start time. But for selected start time, what we end up doing is we calculate it as start of the word k naught plus 3x. 3x is 3 times the number of fails, 3 times the number of failures crushed by modulo L. The reason for this is that The reason for this is so that we heuristically have a position in the audio transcript uh, against which we can match match the word of the true transcript. Every time there's a fail, of course, then we have to suppose or imagine that our position marker for the matching has gone up by 3 because we're trying to match every third word of our true transcript to the best possible matches in our audio transcript. The rest of the code then produces very similar, but not similar, but rather simple. And there's one important addition here. What we do is that we just ensure that uh, whenever the transit uh, is whenever the select start time is 0, sorry, whenever the transit lie falls between min cap and max cap, then we allow the selected start time to stay as it is. But if not, then we set it to be equal to none. And then we ultimately just interpolate along all the none selected start times and use linear interpolation. This then gives the selected start times, which then gives the transitions for our PowerPoint files, which then gets used to produce transition PowerPoint PPTX files inside our transition main directory. And this is then acted upon by the output main Python file, which then produces MP4 files from these PPT files with transition. Here, it slows down the video to 80%, and of course, it produces MP4 file. Let me just show you what the output looks like. The output comes here in this directory. It's these files with the with audio file.
Moral: sharing brings happiness and strengthens bonds of love and friendship.
So this is a very convenient, quick method for producing our text highlighting files, and the whole process from start to finish can produce 25 story text highlighting files in a matter of around half an hour, which is much faster than doing it manually, because manually it would take around 2 days to produce 25 text highlighting files, which can now be done in half an hour.